As we learned from previous video, the steps for the eliminating the effect of atmosphere is all coming down to how do we actually obtain this wavelength dependent extinction coefficient kappa. Okay? So the simplest way to obtain the kappa is by repeating observation of known brightness object across the multiple air mass. Imagine that actually you observed like 5 times of known brightness object. So your standard star, because you already know that actually known brightness object, you already know that actually m sub lambda outside of the atmosphere. So you already know this m sub lambda, and you repeated observation of that particular star 5 times at different air mass of x. Then from this relationship, atmosphere affected the observation of the same star. So that's the m superscript a at 5 different the air masses are all related to the single the extinction coefficient, right? So this a extinction coefficient, that relationship is supposed to be straight line. So y-intercept is m sub lambda, known brightness outside of the atmosphere, and the slope should be extinction coefficient. So by observing the known brightness standard star at many different the air masses, plot this straight relationship, then y-intercept should be the known brightness, the object, I think the magnitude outside of the atmosphere, and slope is basically this k, extinction coefficient. So this relationship, the way that actually we can retrieve the extinction coefficient from the slope of the atmosphere free magnitude versus atmosphere affected magnitude is Bouguer, known as the Bouguer the law. Then we can consider many different possibility of the observing condition. So if the atmosphere is calm and the cloud free and then no changing temperature or pressure, so that actually the atmosphere is really stationary, and because there is no the particular the preferred direction, so no matter where that actually you see that this relationship always just give the straight line, then that straight line, the single line that actually indicating. So, so imagine that actually you are actually observing multiple standard star, and then multiple standard star has the different y-intercept. So one standard star you obtain this, okay? But different the standard star you obtain exactly the same slope but different the y-intercept, because these two standard star has two different of the known brightness, right? If that is the case, then your observation condition is known as the perfectly photometric. What if that actually that your observation condition is not photometric? Then by tracking the relationship, or I think the plotting this sorry, m of a of one particular standard star, sometimes that actually this curve is actually turn around. Okay, this means actually atmosphere is changing condition in that particular part of the sky. Okay, so it is non-stationary, and when you observe two different standard star, okay, one standard star and then another standard star has two different slope, so meaning that actually one standard star is in the south part, or another the standard star you observe toward the eastern part of the sky. And then it indicates that actually that it has the two different behaviors, meaning that actually it's not isotropic and anisotropic. So these are actually all indicating non-photometric. So meaning that actually if your night is photometric, then the extinction coefficient has to be stationary, and extinction coefficient has to be isotropic. So meaning that actually it is not changing and it is not dependent on the viewing direction. How do, how do we actually there are multiple ways of actually obtaining this extinction coefficient at each passband. One is each observatory publish their the standard so-called nominal extinction coefficient at each filter band. You can just simply use and then if especially that actually you don't need that actually the really high the precision observation or that actually your observation that actually was taken believed to be perfect photometric condition, and then you are actually pressed to observe as many science target as possible for the given observation time, so that actually you kind of sacrificed not observing enough standard star. In that case, you can just simply use this the provide observatory provided standard nominal value of extinction coefficient, or you just observe only one time known brightness object. Okay, so known brightness object, one object of known m sub lambda, only one the air mass. Okay, then because you already know the m sub lambda for the particular star, and you can actually obtain that actually that your m sub a can be the calculated can be obtained from your own observation of single standard star at particular LMS. Then from that relationship, you can actually get the slope right away, that proportional constant A. So that's one way. So that can be done by using single observation of standard star. So that is actually slightly better than the first option, okay? But it is not if the conditions are actually changing, and then this is not optimal. Okay? The third the option is basically going back to your own plotting, your own measurement of multiple standard star, and then making this straight line best fit of this 5 point, and from this straight line you obtain the slope. Okay? So that's basically using the Bouguer line of your own multiple observation of standard star. So some meticulous and very careful observers are actually obtaining multiple standard star observations throughout the observation run, even for the given the night. Then by using this multiple standard star measurement can be combined in this way. Okay? Or that actually that using this the observation spread over multiple night can be that actually combined together. So that actually all these of course that actually when you actually the driving this the extinction coefficient from your own measurement, you can actually also compare against the observatory's known values, whatnot. That actually all these the method can be combined all together in a single shot, and then compare that actually the behavior of your own standard stuff, and then whether that actually that should be the I think reasonable in the given context of the observatories they provided with. So there is you can actually build in the cross check, but all in all, somehow you actually get the extinction coefficient one way or the other. Then you can actually eliminate the effect of atmosphere from your measure. Imagine that actually that your this source has a certain spectral shape. So that's the f sub lambda, okay? And you observe this through particular the bandpass filter, and that bandpass filter the response function is this p sub bp. Then when you observe these two, when you observe your source through this bandpass filter, and then ignoring that actually any other effect, what you actually obtain, the recorded spectral shape is this. Okay? Then imagine that actually that you observe this at multiple the air mass, and then that air mass, the atmospheric extinction coefficient has a shape of the shape of the just change the pointer color, and your extinction the coefficient has the spectral shape of this case of lambda. Then when you actually when you observe through the no air mass which is outside of the atmosphere, which means actually x air mass is 0, then you don't have any, you don't see any effect of this atmospheric extinction. Right? But what if that actually the use observed through air mass of the zero point 0.5, then that's that from this the on the recorded the spectrum outside of the atmosphere, that this portion, this part of the wavelength light is actually suppressed. So what you the record is actually this, and the going the observing through the more and more the dense atmosphere, meaning that actually that the longer the path length, the higher air mass, you see that actually that part of the spectrum is actually suppressed even more and more. So what this mean? Does this mean? It means actually your object color, spectral shape, is dependent on the air mass. Okay? So this is known as Forbes effect. The spectrum of your target seen through the atmosphere changes with air mass. So that means actually that the amps of the lambda of A is m sub lambda plus k of x, right? So this and the source magnitude is stationary, but this is affected, and because of the air mass, because that actually the entering the the spectral shape of the source is changing as a function of air mass. And then relationship is no longer linear. So what you typically see is actually, instead of straight line, you actually see the curved line. So meaning that actually that that relationship is no longer can be approximated as the straight linear relationship against the extinction coefficient. So how do we handle this? The easiest way is assume that actually your extinction coefficient and Taylor expand into the multiple the the order. So the extinction coefficient can be zeroth order, and or maybe that this extinction coefficient can be also the Taylor expanded the extinction coefficient can be parameterized in such a way that actually that zeroth order is the constant, second order term, second order coefficient is indicating the next most the dominant the effect, and the second order term is second that actually that the next level of the effect. So in this case, that actually the extinction coefficient zeroth order term is simply proportional to the air mass, nothing else. Right? So there is no color dependent, right? So that specific color dependent that for the given photometric band, that there is simply that actually that the single number that can represent the amount of extinction for a given air mass. And then because of this Forbes effect, that actually that nonlinear relationship is expected, especially for when your object is actually that very sharp the slope, either that actually decreasing or increasing slope, this Forbes effect is actually more pronounced. In that case, you need to actually the consider the next order term, like the first order term or second order term or even the third order term. So usually that actually second order term is indicating that actually it is dependent on the spectral shape of your source. So usually that actually this the first order term is known as the color of your source. So the color of the of your source is actually can be expressed in terms of the magnitude difference in two different paths, such as blue minus visual, visual minus infrared, such as. So you can actually use all sort of the color magnitude of your star here. And usually that actually that the higher order term is actually dependent on the particular the the atmospheric layer or composition, such as if the water vapor amount of water vapor is changing, then actually at a certain wavelength that actually that it is actually causing the variations due to this changing amount of water vapor. Likewise, you can think about the ozone layer, the variation, or temperature or refractive index change due to the slight variation of temperature or the pressure or not. So usually these are actually much minor, I think smaller effect, like at the level of less than 0.1%. Color effect is actually usually in the about few hundredth magnitude, and this atmospheric the extinction that actually zeros all the time is few tenth of magnitude level. So we just ignore typically that actually all the time. Then this extinction coefficient is simply expressed as this. Extinction coefficient is zeros of the term plus the color dependent the first order term. So when we express this, the amps of P, the relationship between the atmosphere affected versus atmosphere free, the magnitude, we can actually express that as this. Okay? Then this K zeros order term multiplied by the air mass and the color dependent term multiplied by the air mass, or the convenience of notation, we actually call this as the extinction coefficient, non-color dependent extinction coefficient, zeros the order, the extinction coefficient, and then color coefficient of. And usually that actually this. So color dependent color coefficient is actually is not changing rapidly for the given observatory. So usually what you do is actually that you usually obtain this from your own measurement and use the observatory provided color term in your here. So this is how that actually we obtain the extinction coefficient.